Hi class, Dr. Condor. I want to talk about two-way tables, and uh, this is going to be a short video, and I just wanted to focus on this one issue. Students have a little bit of trouble with this, but it's a very important concept in statistics. And what we mean by a two-way table is that we're comparing two different variables. So, for example, you'll see here in this example we have variable one, it says major. So we have students taking biology, business, math, and psychology, and we could break that down into just those majors. But we also could break it down further into gender, and that's what they're showing here. Variable two is gender. So we have women and men. And we take biology, we have a total of, 43 people taking biology, but we can break it down further that 32 of those are women and 21 of those are men. So the 53 total, right? 32 and 21. Okay. So same for business. We could break down that 110 women are in business, working towards business degrees, and 87 uh, of men working toward business, and so on. And so that's a nice way to organize the data. Remember when we talked about descriptive statistics, we talked about frequency tables, and this really is a frequency table. We're listing counts. We have groupings, but we have two variables of groupings. And uh, so we can look at this up here and they say, well, you know what? Those two-way tables are also called contingency tables. So contingency tables are a little bit more of like another higher level than just a frequency table and so on. So again, here's a definition: two-way table shows that the row variables, right? You have the row as one variable and columns as another variable. And here's an example. They're taking part of that table and they say, okay, it looks like more women in biology, more women in business, but well, that's because there's just more women in general in the data collection. We have 142 total women, 108 men. So we can't really right now say that, women like biology better because look, there's more women. And well, again, in a lot of colleges, there's a larger percentage of women there than men. So we have to figure out more of what we refer to as expected frequencies and compare those. But there's one thing in particular I want to focus on. And here's another example. You can even break tables down into more groupings. You have an ACME treatment, whether it's mild or severe, whether the person was cured or not cured. Okay, we got that broken down two ways there. And then now here, also, were they using the old treatment or new treatment? So this is even, showing that you can further break down these contingency tables into more than two different types of groupings. Okay, again, so we have whether it was the rate of severity, right, of treatment, whether they were cured or not, and then the type of treatment that they had. So we have three different things we're talking and comparing about. And then they show another example here you can look at. But let's go ahead and move on to typically where students have trouble is when they talk about these polygraph tests and these drug test things here. And here's an example. It says that suppose the government gives a polygraph test to 1,000 applicants for a security job. So we would, want to make sure they're a person that maybe is not on, drugs. So they do the drug test and they say, further suppose 990 of these 1,000 people tell the truth on their polygraph test. So up front, we're saying that we know a little bit about what's going on here, right? So 10 people lied, right, out of these 1,000 people. Now, for the test itself, right, that's 90% accurate. Now, of the 10 people who lied, the polygraph correctly identifies 90% of those, meaning that 9 failed the test and 1 passed. And 990 people who tell the truth, 90% of those are 891. Now, it's kind of getting confusing because I just looked up here about this 90%, and then they got a 90% here. So, you know, it's starting to get cloudy on what are we talking about. Now, so let's say we want to organize this. And one way that you can do that is to do this little kind of tree diagram. And then again, students typically don't respond well to this, although some think it's a little bit easier, but most of them like the tables. So what I'm going to do then is take this information that's here and put it into a two-way table. And we're going to put this away. And so I started putting this together to speed up the process. So I made this table where we have 1,000 people there, right? And then we know that they're telling us that 10 people lied, right? 10 people lied. So we have 900. Okay. We have 990 lied. 10 did not lie. Okay. So we have, of the ones that lied, right, we have lied and did not lie. Okay, did not lie. So how many lied here? Got that backwards. Yeah, got that backwards. So the did not lie was 990. Let's go back in. Change that. Okay, so 990 and 10. All right, there we go. That's better. So it did not lie, 990. Lied, 10. All right. So once we get that, right, so we got this information and we don't need that anymore. What we want to do now is talk about the lie detector test, that it's not accurate. Okay, it's not 100% accurate. So these polygraph tests, again, according to this example, it identifies correctly 90%. Okay, 90% of the time it's correct. So if we want to say, okay, let's test the ones that lied. Tested that they lied. Well, it's only going to test 90% of these, right? That it lied correctly. So 90% accurate, right? So in other words, 90%, 0.9 times 10 is going to give me 9. So in other words, they lied and it tested that they lied. So out of these 10, right, it got 9 of them right. Out of the 10s that lied, did not. Well, how many does that leave left? 1, right? So one person lied, but they didn't get caught on the machine, right? Now, let's look at these people. Say, did not lie. It's 990. So we need to, again, 90% accurate. So tested that they lied, right? Well, let's see. They didn't lie. Tested that they did not lie, right? So it's 90% accurate, right? Times 990 is equal to 891. Okay, so 800. So you got to be careful on that part. That's here. We did this one first. She tested that they did not lie. They didn't lie. Got 90% of these correct. We put that right there. So then how many's left? Right here is 99. Right, 10% of this big group here, 10% of this group, right? It's messed up on it. So when you hear about the lie detector tests, uh, why they don't use them all the time because uh, you know they have problems, and yeah, it seems like it's working pretty good over here, but that's not the issue. It's look how many of them here of these 1,000 people. Okay, it only messed up on one of the liars, and you say, "Oh, that's so good," but look at this: 99 people it messed up on, where in a sense it's almost telling them that they're lying, right? It tested that they lied, but they didn't. So you're accusing innocent people. So if somebody that's guilty, well, they don't get caught, that's because there's only one of them. We're saying that's really not that bad. We're doing pretty good. But look, if we accuse 99 people that didn't lie, so they talk about a false positive. It's positively testing them as lying. It's a false positive, right? That's not very good. Okay, so that's the big problem there. So total of these were 108, right? Total of these 892. We had the total of 1,000, right? So these were our totals on that. But that's our big concern. So that's something may help you understand the idea of the lie detector tests, and they use them, but they're not really 100%. And this is really not good because if these people were going for a job, here's 99 people, right, out of 1,000. These people were all legitimately maybe good workers, but the lie detector test messed up. Now these people can't get a job because of the messed up test. That's not kind of not fair overall. And then if you miss one, right, again, that's just kind of your philosophy on that. So, but we're going to stop there, and that's going to be it for this video.